All right, students, let's get right into our lecture on energy and work and look at some of the basics. Now, when we look at an energy model for any particular system, typically when we talk about energy, I do it every time, we use this symbol E to represent energy, and that can be referred to as total energy in most cases. And so there are several different ways to, or different kinds of energy. Of course, we have kinetic, potential, gravity, potential, elastic. We have our spring potential. We have energy thermal, energy chemical, and so forth, okay? But typically when we say the total energy of a system, we use the uppercase E, and notice that the total energy of any system is going to be the total of all other energies of that system, with kinetic, potential, thermal, chemical, and so forth, okay? Internal energy, we could throw that in there too, and that would also be considered part of the total energy. Now, just some important things to remember about the different forms of energy. Of course, kinetic is energy of motion. Anytime an object's moving, it has kinetic energy. If it is not moving, it does not have kinetic energy. It has zero kinetic energy. Gravitational potential is a type of stored energy, and it is always going to be connected with or associated with the object's height above the surface of the earth, okay? And you've got to realize that. And an object sitting on the ground on the surface of the earth has zero potential energy, okay? Because it does not have it is not above the surface of the earth, it is on the surface of the earth, so therefore it has zero potential. You have elastic or spring potential. Sometimes they'll put UEL or US for spring. Again, that's another form of stored energy, but we are looking at the amount of energy that can be stored in a spring, or it could be a rubber band, okay? Any type of elastic material. It doesn't have to be a spring. It can be anything that's elastic, okay? Thermal energy, again, we're looking at the sum of the kinetic and potential energies of all the molecules in an object. Now, sometimes we might refer to this as internal energy. They are very closely related, okay? And then, of course, chemical energy is another type of stored energy, and it deals with the energy required to break or create bonds, okay? And then we also have nuclear energy, and of course, nuclear energy is the energy that is stored in the nucleus of an atom. So when we split or when we fuse atoms, you don't have to just split them, you can also fuse them. Then we have a release of this nuclear energy, and it is tremendous, okay? All right, now, so when we look at a little schematic, or not a schematic, but a Venn diagram, I guess, similar to a Venn diagram, a model, we'll just call this a model, we see that there is a relationship between kinetic and potential. And typically when you have high kinetic, you have very low potential, and you have very high potential, you have low kinetic. But these two also are related to chemical energy, because chemical energy is a form of stored energy. But when that energy is released, guess what? We call it the kinetics of the reaction. In other words, molecules begin to move, atoms exchange electrons with each other, things begin to visibly happen. Most time we can see this occur, okay? Not always. It's not always, an explosion or light given off. But, sometimes we don't see it until maybe after some time has passed. But notice there is a relationship of potential and kinetic to chemical. And then, of course, these all play into thermal energy, okay? All right. So energy transformations, it takes chemical energy to lift those barbells, and you have to work against gravity. Actually, the work done by gravity on the barbells for the lifter to lift them is negative because it's going in the opposite direction of gravity, okay? Same thing here. We have elastic potential energy of the diving board. Of course, the elastic potential energy is going to be at maximum when it's right at the point of, I guess you could say, the rebound of the board. And the diver, of course, the board throws the diver up, and the diver jumps and does his wonderful dive. Now, so we have a child on a playground swing, and it's motionless at its highest point of his arc. What energy transformations takes place as he swings back down to the lowest point? All right, would it be kinetic to potential or potential to kinetic? So what do you think? Well, it would definitely have to be potential gravitational to kinetic, because what pulls the child on the swing back towards the surface of the earth? It is gravitational potential energy, and of course that energy is being changed into kinetic, okay? A skier sliding down a gentle slope at a constant speed, what energy transformations is taking place? Well, he's sliding down at a constant speed, so we have what? We have kinetic energy, or potential energy, being converted into thermal energy, because notice it's at a constant speed, and so if it's at a constant speed, then the potential energy should equal the kinetic energy, and potential energy is doing what? Being converted into energy thermal because of the friction between the skis and the snow. All right. Now, when energy is transferred between systems, or energy can be transferred between a system and its environment through work and heat. Now, please understand the differences in work and heat. Now, when we look at work, work is actually the force applied, and we'll get to this a little later, on an object through a given distance, okay? Now, work is a scalar quantity. In other words, it's actually the dot product, okay? It's not the cross product, the vector product, but it's the dot product of an object's, of the force applied on an object through a given distance. And what do you mean a scalar quantity? In other words, it only has magnitude. Now, in other words, the angle at which the force is applied is all we are concerned with. Now, what do you mean by that? Well, in other words, we're not concerned with north, south, east, and west, okay? All we are concerned about is the force being applied to the object at a 0 degree angle, at a 10 degree angle, at a 15 degree angle. What is the angle at which the force is applied on the object, okay? You could be going up, you could be going north and still applying, force on an object and an angle, okay? That's the angle we're concerned with. We're not concerned with north, south, east, and west, okay? Now, heat is a process. In other words, the transfer of energy between a system or from one form to another is what we call heat. And many times we confuse heat with energy. In other words, we think that heat is energy. Well, no. Heat is the process of transferring energy, okay? It is not the energy itself. Many times we'll say, all right, go turn the heat up. We'll be sitting in the house and it's cold, and we'll say, go turn the heat up. Well, okay, that's really not a correct use of the word heat, because what are we saying? Well, in other words, we're saying we want the room warmer, okay? And so in order to do that, we've got to increase the energy in the unit. We've got to cause the unit to create energy, and it does it electrically. The electrical energy goes into the heating coil. It heats up, a fan blows across it, and it moves the warm air into the room, okay? So in a sense, we are transferring energy, okay, from the unit to the room, but again, when we say turn up the heat, really what we're doing is saying turn up the energy, increase the energy, okay, in the room, all right? Now, energy transfers and work. Well, again, when we look at the different forms here, we've got kinetic, we've got energy thermal, which actually started out as potential chemical, and then here we see elastic potential energy, the little boy is shooting a rock, okay, hopefully not at someone. Now, tow rope pulls a skier up a slope at a constant speed. What energy transfer or transfers is taking place? Okay, well, he's pulling them up at a constant, pulling it up at a constant slope. But we also have friction taking place too, don't we? So we have both A and C. So work is being converted into potential energy. You say, what do you mean? Well, as you go up, U of gravity is increasing, okay? Because remember, it has to do with how high above the surface we are, okay? All right. And then, of course, work is also being converted into thermal energy from the friction, okay? Now, so how do we write an equation for work? All right, well, this is how one way we can write it. We say that the total energy of a system changes by the amount of work done on it. And what is that equal to? Well, the total energy, and you need to put this on your formula card, is equal to the total, change in kinetic. So the change, and by the way, it's change and change in total energy, is equal to the change in kinetic plus the change in potential of gravity and change in potential of spring plus the change in thermal energy plus the change in chemical energy plus the change in electrical energy plus the change in nuclear energy. I mean, we could just go on, is all equal to work, okay? In other words, what we could say then is delta E is equal to work, right? Now, if no energy is transferred, and of course work can increase or decrease the energy of the system, no duh. More work you do, then you're going to see an increase in some of these others, okay? Now, if no energy is transferred into or out of the system, that is an isolated system. In other words, if work in is equal to work out, then it's basically, what have you got? It's equal to zero, isn't it? And so that's considered to be an isolated system. So the total energy of an isolated system basically remains constant. So what are we saying? We're saying that E is equal to work, okay? In other words, they're equal to each other, all right? Now, let's look a little bit more at work. So, and I already defined this for you. Anytime an external force is applied to an object and it moves from point A to point B, in other words, it is applied through a given displacement, and I don't like using D there. I wish they'd have used change in X, okay, or the integral of the force with respect to dx, and because work is actually an integral. It's the integral of the force with respect to the change in displacement. In other words, if you take it and plot it, and you got F and you got X down here, and you do that, it's the area under the curve, okay? And we do that in calculus-based physics, okay? But simply written, calculating work algebraically, provided that the force is constant. And if we have, and that's important, if the force is constant. Now, if it's not constant, we have to do an integral, okay? All right. So, but if it's a constant force, algebraically, we can say then that work is equal to the force times the change in displacement. I don't like using D there. I wish they'd use delta X, okay? The direction or the displacement. I kind of understand why they do that, because displacement D, but you got to understand something. The displacement is actually X, and that has to do with direction. So I kind of understand why they did that, because remember, it's a scalar quantity, okay? Please remember that, all right? It's a scalar quantity. It's the dot product. So the amount of work done then, the amount of work is equal to what? Well, anytime you multiply Newton times a meter, you get a joule. Of course, that's named after James Prescott Joule. And I need to take a quick break, okay? Okay. All right, so please write that unit down on your formula card. the joule, 1 joule, is equal to a Newton times a meter. And it's the amount, it's actually defined this way. If you apply 1 Newton force and move to an object and move that object through a distance of 1 meter, then you have done 1 joule of work, okay? All right, so please write these formulas and these units on your formula card. So Sarah pushes a heavy crate 3 meters along the floor at a constant speed. She pushes with a constant horizontal force of magnitude 70 newtons, okay? How much work does Sarah do on the crate? Well, that's easy. You move it 3 meters with a force of 70 newtons, you do 210 joules of work, okay? All right, now, but what about when force is applied at an angle, okay? Well, then we have to take into consideration the angle, and we do this by taking the cosine of the angle and multiplying it by the force. Now, needless to say that when a force is applied to an object at an angle, then that means the amount of work is going to be less, okay? If you think about it, because the cosine of 0 is 1, and anything above an angle of 0 is less than 1, is a decimal. So when you multiply that times a decimal, the number drops, okay? So it's better if you want maximum work to apply the work or apply the force to the object at a 0-degree angle. Of course, sometimes that cannot be done, okay? We understand that. Now, which of these, a constant force F pushes a particle through a displacement of delta R? In which of these 3 cases does the force do negative work? All right, notice right here that the displacement is, and again, if we were to draw our coordinates there, that looks like about 100 and I don't know, 40-degree angle, thereabouts, 50-degree angle. The cosine of 150 is negative, isn't it? And then look right here. Here we have a negative, we got negative force but being pulled in a positive direction, the displacement is. So which one would it be? Well, it have to be both A and B. Now what about C? Well, they're both going in the same direction, so the work has to be positive on C, okay? All right. Okay? Which force below does the most work? All 3 displacements are the same, okay? I think it's pretty obvious it'd have to be that one, right? Okay, absolutely, the 6 Newton force, okay? Now let's look at kinetic energy. Of course, again, the energy of motion, and of course there is translational and rotational energy. And we define, or we calculate the kinetic energy. It's actually derived from our work equation, okay? And we won't go into all that, but that's how it's derived. And by the way, work is equal to kinetic energy, but work is equal to the change in kinetic energy, but work is equal to the negative change in potential energy. And you say, well, what do you mean by that? Well, work and kinetic energy are the same, okay? They're one and the same. However, if you're doing positive work, in other words, if I do positive work to lift a stone, then the amount of potential energy, the amount of gravitational potential energy is negative, okay? Why? Because I'm going in the opposite direction of gravity, okay? All right, now, so kinetic energy, translational, this is translational right here, translational, okay? Translational is K is equal to 1/2 mv squared. Notice that squared right there. And rotational, it would be 1/2 times the moment of inertia times the angular velocity squared, okay? All right, so that's 2 different ways we can calculate the kinetic energy of an object, either in a linear direction or in a rotational motion. All right, ball A has half the mass and 8 times the kinetic energy of ball B. What is the speed ratio? Okay, so it has half the mass, but 8 times the kinetic energy, okay? All right. So ball A, what is the speed ratio of VA to VB? Okay, well, half the mass but 8 times kinetic energy. Well, do the arithmetic. What are you going to get? 4 times as much, okay? All right, so ball A has what? What is the speed ratio of VA to VB? Well, then you say, well, now how can that be? Well, you got to realize something, that you're dealing with a square root there. Okay, squared. Okay, all right, square root. Now, all right, potential energy. Potential energy, as we've already said, is stored energy. We can look at it as gravitational potential, elastic potential, chemical potential. Okay. But here we're going to look at gravity and elastic. Now, forces that can store useful energy are referred to as conservative forces, and of course those that cannot store it and lose it are called non-conservative. And they talk about friction is a force that is non-conservative. Okay, in other words, once you deal with friction, the amount of energy that is produced by friction is gone. Okay, you can't get it back. Okay, you can't get it back. Now, okay, gravitational potential energy, again, we were talking about this a little earlier. I'll have to do positive work to raise the book. The work done by gravity is negative, okay, because the book is going up. Now, when we drop the book, if the book is going down, the work done by gravity is positive. The work done by my hand has to be negative. Okay? All right. Okay? All right. And we write the equation. Here's another equation for your formula card. Potential energy, gravitational potential, is the mass of the object times acceleration of gravity times the y, and actually we should say change in y, the change in the height above the surface of the earth. And of course, anytime an object is at, in other words, if you look at the gravitational potential energy of this person right here in relation to right here, well, his UG right here is equal to 0 joules, okay? All right, it's equal to 0 joules, okay? Why? Because he's on the surface, all right? Notice as his potential goes up, as his height goes up. Okay, you double the height, you double the potential, gravitational potential energy, okay? All right, now, rank in order from largest to smallest the gravitational potential energies of the balls. Well, it's obvious this one right here is going to have the greatest. You say, yeah, but it has a velocity of 0. It does not matter. Remember, gravity is not dependent, potential energy is not dependent on gravity, on velocity, it's dependent on gravity and how high above the surface we are, okay? So 3 is highest above the surface, so it's going to have maximum potential. Which would be the next? Well, wouldn't those two be equal and this one be the least? Well, you know what? It most certainly is. 3 is greater than 2, which is equal to 4, and is less than 1, okay? All right, I hope that makes sense. Now, elastic potential energy, again, when you have a spring at equilibrium, of course, there's no movement, there's no potential energy. But when you compress this spring, then guess what? The potential energy, based on how much you compress it, will increase. And now, a lot is dependent on the type of spring that you have. If you have a very weak spring, well, you know, you may stretch it or compress it 2 meters, and it just may not have very much elastic potential energy. But if you have a very stiff spring, then you're going to have a tremendous amount of potential energy when you compress it or stretch it, okay? So notice here, this is very similar to our kinetic energy equation, isn't it? It sure is. The only thing different here is that K, that is called the spring constant, okay? That has to be given to you, the spring constant. You could solve for it if you knew this and knew that. Okay, the spring constant. And of course, X is the change in displacement, okay? Change in displacement. All right. Okay, so there's another equation. This is elastic potential, U subscript S, that you can add to it. And yes, the units are still joules, y'all. Anytime we're dealing with energy or work, it's joules, okay? Okay, everything is in joules. How do we really define, energy? Energy is the ability to do work, okay? That's how we define energy, the ability to do work. All right. If you can't do any work, then you don't have any energy. Okay. All right. Now here they ask 3 balls are thrown from a cliff at the same speed, which ball has the greatest speed just before it hits the ground? Well, they all do. And you say, well, how can that be? All right, look, folks. Remember, when we release an object, regardless, all right, it comes under the influence of gravity. Okay, it comes under the influence of gravity, and since they're all moving from the same height, then they have to be at the same speed when they hit the ground. Okay, and you say, how's that? Well, mgy is equal to 1/2 mv squared. Okay, all right, they're all going from the same height. Okay, all right, now thermal energy. Thermal energy, of course, has to do with what we call vibrational motion within a substance. And when these molecules vibrate, when these bonds begin to stretch or compress, you either have energy released or energy absorbed. Okay? And these objects, this type of energy is a type of what we call internal energy. Okay? And so the more vibration of the molecules and the atoms in the molecules, then the greater the energy you have, okay? All right, now, so we can define that by using this equation. The change in energy thermal is equal to, and you say, well, how do we create internal thermal energy? Well, by friction, by kinetic friction. That FK, now don't forget, is kinetic friction. Okay, and of course it's dependent on the distance that it moves. And you say, well, why is it dependent on the distance? Because look, y'all, that is equal to work. All right, and this right here, if you remember, I forget what chapter it was. Was it chapter 6 when we did friction? I can't remember for sure. All right, now, and so friction kinetic is equal to what? The coefficient of kinetic friction times force normal, or friction kinetic is equal to the coefficient of kinetic friction times mg, right? All right. Okay. And so remember that for your equation sheet. And yes, it's still in joules because it's energy. Okay. Now what about the law of conservation of energy? Let's put all this together. Well, when we look at an isolated state system where the work is equal to 0, in other words, the work in is equal to work out, well, again, we start summing up all of our energies here. As you see in the top equation, notice right here, the change in kinetic plus the change in gravitational potential plus change in potential elastic plus change in thermal is equal to the work. Well, then let's rearrange this equation. Let's break these apart and do K final minus K initial, and UG final minus UG initial, and etc. so on. And let's put this thing together. Now notice we left this one as it was, okay, because remember that has to do with friction. But you could say E final minus E initial. You could break it apart, okay. But we choose to leave it that way. Why? Because this is equal to work, okay. All right, it's right there. See it? Right there. All right, now, so we take the final kinetic plus the final gravitational plus the final elastic plus the change in internal energy should be equal to the initial kinetic plus the initial gravitational plus the initial elastic plus the work, okay? And if it's an isolated state system, guess what? The work is equal to 0, so the equation simplifies to this right here. Okay? And so you might want to write these two different equations on your formula card. Okay? This one and then the one for an isolated state. Okay? What we call an isolated state. All right? Okay. Now choosing an isolated system again, we choose the ball and the earth as a system so that forces between them are internal forces. There are no external forces, okay? So it's isolated. Same thing here with the object going down the ramp. External force the ramp exerts on the object is perpendicular to the motion and does not and so does no work. The object and the earth together form an isolated system, and so on, okay? So I'm not going to sit here and read these to you, but you can see how we determine an isolated system, okay? So if we have a spring-loaded gun shoots a plastic ball with a launch speed of 2 meters per second, the spring is compressed twice as far. The ball's launch speed will be what? Well, I hope and pray that you say 4. And you say, why? Well, because look, it went twice as far, okay? If you double X, oh, now wait a minute. Wait. Let's make sure on that. Let's see. Yeah, because both of these are squared. So, yeah. That's right. Okay. All right. Okay? All right. Now, energy and its conservation, of course, we've got kinetic, we got gravitational, and elastic potential. And again, remember that kinetic and potential are opposite to each other. So if you have high kinetic, you have very low potential. If you have very high potential, you have very low kinetic, okay? Well, what do you mean by that? Well, how does that work with a spring? Well, when the spring is completely compressed, it has very high potential, but zero kinetic. When it's completely compressed, it's not moving. Or when it's completely stretched, when you've stretched it to as far as you want to stretch it, it stops moving, but it has very high potential, but it has zero kinetic, okay? All right, now, all right, so energy and its conservation, again, we look at these equations we've kind of already looked at. We've already looked at this one. That's how we find the change in thermal energy. And then, of course, to find the total energy and the initial total energy, again, when we look at the law of conservation of energy, notice because why? Work is equal to 0, okay? And so this is what our equation looks like, that the total final will be equal to the total initial, okay, plus that right there, any friction that creates thermal energy, okay? All right, what about energy in collisions? Well, of course, we've already talked about collisions. I believe it was in Chapter 8 or Chapter 9. You have collisions, perfectly inelastic and perfectly elastic collisions. Remember that when we have when we're looking at momentum is always conserved in all collisions. However, only mechanical energy is conserved in an elastic collision. We talked about that when we were talking about momentum, okay? So please remember that. And of course, in an inelastic, some of it is converted to thermal energy. So how then do we create our equations to determine or how do the energy equations apply to momentum? Well, they apply exactly the same way because look, an object moving is kinetic energy, isn't it? Okay. So basically, how would we find the kinetic energy of this object initially to what it would be finally when you have the collision of two objects? Well, can we not, since we're dealing with an object that's moving, it has velocity, can we not use the kinetic energy equation? Well, sure we can. So we can say the initial kinetic energy is equal to what? The final kinetic energy of the two. And that leads us to these equations right here, and I want to go ahead and move to these equations, and you can go back and read over this, is that from our kinetic energy equations dealing with momentum and conservation of momentum, we can find the initial velocity, the final velocity of object 1 and the final velocity of object 2 using these equations right here. And so please write them on your formula card, okay? So this is the final velocity for object 1. Now this is after they collide. Final velocity, okay? Of object 1. Excuse me. Excuse me, I'm sorry. Okay, and here's the final velocity of object 2. Okay. And that's how we find it. All right. And notice that they are both determined on the initial velocity of object 1. Okay. But please pay close attention to the signs here. Pay very close attention, all right? Okay, now, what about power? Again, power, now we've talked about energy, the ability to do work, but what is power? Power is the rate at which energy is used. Here they say transformed or transferred. Okay, we can live with that, but in other words, it's the rate at which energy is used, and it is actually a derivative. It's actually the derivative of a work with respect to time, if you want to really get technical with it. Because it's a rate. Remember when we took calculus, anytime we're dealing with rates, we're dealing with derivatives. Okay? And so if we take the change in total energy and divide it by the time interval, we get what is called power, and the unit for power is the watt. Okay? And yes, a watt is the number of joules per second. And how do we define that? Okay. Anytime 1 joule of watt is expended during a time interval of 1 second, then we have used 1 watt of power. Okay? 1 watt of power. So we can write it this way, and we can write it this way. Notice that these are equal to each other. Okay? Now more formulas and more units to put on your formula card. And we can also write it this way. If we take work being the force through a given time interval, the force applied through a distance, because that's what work is, notice what it becomes. It becomes what? The change in displacement through a change in time interval. Well, y'all, that's velocity. So we can also find the amount of power if we know the force applied and we know the velocity at which that force is applied. Okay, so we can find power. It's the same unit, watts. If you do the arithmetic, you'll see that it comes out to be the very same units. Okay, so here's another equation. So there's 3 equations for power, and actually these are the same equation. It's just using change in total energy and work. Okay, remember they're equal. All right, now four students run upstairs in the time shown. Which student has the greatest power output? Of course, it would be this one. Why? Because it has the lowest time interval. Okay, you say, well, this one has a lower mass. Well, it doesn't matter. Let's see, is the height the same? I believe it is, yeah. But again, the time interval here, is it 10 meters? Yeah, 10 meters, all right. So the time interval is less, okay? All right? Okay. And that's it.